So, let's go ahead and plug this and get this up on the board, whiteboard. Okay, so today I'm going to quickly go over proof by induction. This is a useful tool in mathematics for proving something. It's basically the laziest way I've seen to prove basically series. So if you follow this, then hopefully it will give you edge in Calc 2 because they love asking to prove this question, which was question 3 from our homework, which is 1 plus 2 plus 3 plus 4, well, dot, 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 n minus 1 plus n, I don't need those parentheses there, n is equal to n times n plus 1 over 2. I didn't have that. That's the answer for question 3, by the way. It's n times n plus 1 over 2, which should be, which that simplifies out to n squared plus n over 2, which becomes just O of n squared, right? So that's question 3 on our question. But why? How can I prove that these two things are equal? Well, we can do so by what's called proof by induction. Proof by induction is a two-step proof, which is, and the steps are as follows. You prove base case. You're going to hear that term a lot, the base case, because we're going to be working with recursion, and we use base cases in recursion a lot. The base case is basically the thing that is super easy to kind of prove, and kind of our starting point. In this case, we'd want to prove this series for just 1. 1 plus nothing else, just itself. Does that hold there? And then the second, and I'll get into the second step. So let's go and first prove that base case. So because the formal thing is that this is equal to like a series of up to n. I is equal to 1, I, and then sum up into n. So I'm saying n is equal to 0. So that would just be 1. So we're going to prove that this formula works for 1. 1 is equal to n times n plus 1 over 2, right? And we're letting n be equal to 1, right? So 1 times 1 plus 1, so that top becomes 2. 2 over 2 is 1, right? So we proved it. And just to give you clarification, we don't have to manually prove it for the second case, which is 1 plus 2 is equal to 2 times 2 plus 1 over 2, okay? These cancel out, so we're left with 2 plus 1 is equal to 1 plus 2, right? It's 3 on both sides there. So anyway, but we've proven that that the base case works, that this equation, this series, holds true if the series starts at 1, okay? So what is part 2? Because part 2 is the important part. Part 2 says assume true for k. Let n equal to be k. Assume it's true for some number k. Assume that if it's true for k, prove k plus 1. What does that mean? What we're going to do is that we're going to assume that we're going to choose some arbitrary number k. And actually, we're never going to choose a number. We're just going to say, we've chosen a number, let's call it k, and it's good for that. And we're going to say, if it works for k, then we're going to assume it's true for k, and we're going to prove that k plus 1 works, assuming that k worked. You'll see how that feeds into that. Why do we need to assume that it works for k? Now, the reason this is what we need is because it's going to work like dominoes. We've proven it works for 1. And if we can show by using that it worked for 1, it worked for 2, then we've proven 2. And that would just simply show that if we have 2, that would prove 3. If 3 would prove 4, 4 would prove 5, 5 would prove 6, and so on and so forth. So the idea here is that we're assuming true for k, and we're going to prove k plus 1. What would that look like? That means just rewriting this equation in terms of, instead of having n, we're going to rewrite it in terms of k plus 1. 1 plus 2 plus 3, dot, dot. That's a weird 3. 3, dot, dot, dot. And now we have k plus, and again, I'll just actually, k plus k plus 1, right? Notice instead of being n minus 1 plus n, it's ending at k plus 1, right? It's the same series. I've just simply substituted a term instead. And now, same over here, we had n times n plus 1 over 2. So wherever we had an n, we're going to substitute a k plus 1. Okay? And why? I know that sounds weird, but trust me on this one. Because the main point of that is that we've got that dot, dot, dot. And we got to get rid of that dot, dot, dot. And we can through this method. K plus 1 times k plus 1 plus 1. I know that's a weird way to write it, but it's what we need. Over 2. Okay. So this is where our proof by induction works, because we have to go back to that first part, which is the assume true for k. That's our cheat code here. We're going to assume it works for k. So if it assumes that works for k, that means we can use this equation over here that we say we assumed it worked for all the way up through instead of n for k minus 1 and k, right? We can assume. Now, what does that give us? Well, this is an infinite series. Or rather, it's not an infinite series, it's a finite series. And this part, we can rewrite now. We can rewrite that part, because that's 1 plus 2 plus 3 plus 4 all the way up to k minus 1 plus k. So we rewrite that part as, so we're going to rewrite this entire equation. That's going to be, instead of that, we're going to rewrite that as k times k plus 1 over 2. We can do because we said it works for k. We said it works for k, so now we're trying to prove it works for k plus 1. Plus k plus 1 is equal to, so there's that piece, right? And then on the other side we have k plus 1 over k plus 1 plus 1 over 2. Now there's a reason I'm going over this, which I'll tell about later. So this is a bit annoying over here. I've got this big fraction over here, I've got this 2, and this guy does not have a 2. And I'd very much like him to have a 2 so that I could merge those fractions, so that they could both be fractions and I could merge them together, right? Make sense? So I'd very much like to do that, so I'm just going to use some of those annoying algebra tools that you're like, oh yeah, that's a thing I can do, which is that I'm going to multiply this by 1. I'm going to cheat and multiply it by 1 by saying I'm multiplying it by 2 over 2, right? You can do that, remember? And now that allows me to put both of those sides together. Okay, in fact, I will just simply rewrite this right now over here in front of us, plus 2. Okay, and that will be over 2. Okay, so now this part also is a bit weird, but not because just because of what we're pulling out. We've got k times k plus 1 and 2k plus 1 over here. So over here we have a common factor, k plus 1 and k plus 1, right? It's a common factor. I'm so sorry I'm subjecting you all to my terrible handwriting. I should have gone into medical school with this handwriting. So anyway, so I'm going to extract that k plus 1 factor out. What does that mean? I'm going to rewrite this equation to be k plus 1, right? This is that common factor over there, okay, times k plus 2. And so you get this rather than So what's going on here is rather than foiling, right, you can convert from this to this by, rather than foiling, to doing k times k plus 1 and 2 times k plus 1, right? If you don't foil it, you can get to the above term. Over 2 is equal to k plus 1 times k plus 1 plus 1 over 2, and we can just simply rewrite this 2 as a 1 plus 1, right? And then I'm just going to throw some parentheses around there for good measure, and look, they're both the same equation. So what does this mean? It means that if we have some term, if we assume that it works, and that this series is true for 1 through k, it's going to work through k, it's going to work for 1 to k plus 1. So we've proven that if it works for 1 to k, it works for k plus 1. That means that since it worked for 1, it's going to work for 2. So 2 is proven. Since 2 is proven, we can assume it works for 2 and know it works for 3. And so we know it's true all the way up to whatever arbitrary number we want. That's proof by induction. Now the reason I bring this up is because when we go over when you go over recursion, a lot of recursion and to prove that your recursion works, a lot of times the easiest way is through this process. With recursive, you basically, when you do a recursive function, you kind of have a base case, and then you have a recursive case, which we'll get into on a different day because I don't want to take up too much time here. Want to make sure I get plenty of time to speak with everybody. So you prove that, hey, it worked for this term this time, and then everything we do makes progress towards that base case. They're very, very similar processes to prove. Now, now this is a very common question, by the way, in Calculus 2 classes, I believe. Or something that deals with infinite series. A similar question, of course, asks, what is question 4, and you prove it exactly the same way, which I'm not going to do in the class. I'm just saying you use the same tool, 1 squared plus 2 squared plus 3 squared, to n minus 1 squared to n squared, right? That is equal to, I think, did anybody look up what that equation was? Yes?
It's n times n plus 1 times 2n plus 1 all over
6, yeah. And n plus 1, it's always that last term that gets me. It's 2n plus 1, you said, right? Right? 2n plus 1 all over 6. I remember the n plus 1, the 2n plus 1. And so, again, you would again prove that by induction. What you would do is you'd assume it was true for some k. You'd prove it works for 1, which it does. Then you'd assume that it works for some k value, and then you'd basically substitute that on the right-hand side, on the left-hand side, and then merge those together and make it look like the right-hand side. It's a very useful tool for doing this kind of stuff. But by the way, that's, again, your answer for number 4, which we have 3 n's on top, right? So that's n times n times n. That's 3 n's together, so it would be O of n to the third. Okay? Now, a couple things with that for those of you that looked up Bogo sort earlier, and I just wanted to make some very quick corrections that are very common. So first off, for Bogo sort, some of you put O of infinity for the worst case scenario, or O of infinite. The technical term we would use is indeterminate or undefined. We can't figure that out. Now, with Bogo sort, again, we explained that earlier. You're just simply shuffling the deck of cards until it's sorted, right? If you're really unlucky, right, what's going to happen? It never gets sorted. So that's why that comes in. So when I say average case, I'm assuming that basically that we're only hitting each possible permutation once. Okay? For solving the average case, what you want to keep, if you look that up on Wikipedia, it's going to have some number that's like O of n plus 1 factorial, which is, yes, that's true, but that's also a weird quirk of how that works. What you want to keep in mind of how you get to that point is that the operation of shuffling is O of n time. To shuffle something takes O of n time, right? You have n cards, you got to move them all around. And the operation of checking if something is sorted also takes O of n time. So take 2n time to shuffle something and then check if it's sorted. To check if something's sorted, you go from left to right and basically say, hey, is every item less, does every item come before the item that it comes before? So you have to do that for so you have to do 2n operations. 2n operations times the num of permutations. Okay. Now, with regards to the question, the last page where I'm telling you, hey, analyze your own code. Keep in mind you've got basically one of three choices: O of n squared, O of n, and O of 1 for the most part. Okay. You count how deeply nested the loops are. That's a good way to do that for this kind of way. If you solved the permutation problem by sorting it, then you're using a sorting algorithm. Look up what the runtime for a sorting algorithm is. You're using timsort, by the way, if you're sorting it. If you're sorting, Java uses two different sorting algorithms by default. Timsort is the one that is used for objects, which is a variation of merge sort and insertion sort. You probably didn't run this runtime, so honestly, you've got a 50% chance if you're just totally guessing. The most common mistake I see is for the last question, which is this, where in the last question, you're almost always going to use a list.remove statement, right? In the last question, you probably wrote your last problem on the ArrayList homework with the list.remove. This is an O of n operation, right? So you got to treat it, or another way. So what I mean by that is that remove operation has a for loop inside of it, right? So when you're doing your analysis, just remember that list.remove hides a for loop in a separate method. Make sense? So, that's just a common mistake I see, to not take that into account. And thus you say that it's much, much, much quicker than it actually is. So, all right. I'm going to go ahead and stop recording, and I'm going to go from that way because